The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our first webinar as part of the Technical Webinar Series 2021. We are about to start in 1 minute. If you want to ask questions, please use the Q&A button, and Sergio will cover as many questions as possible at the end of the presentation. This webinar will be recorded and will be available in our technical library at www.I-Gard.com. Today's webinar is entitled Resistance Grounding for Data Center Applications, presented by Sergio Panetta. Sergio Panetta is the VP of Engineering at I-Gard Corporation. Sergio is a graduate of McMaster University with over 3 decades of electrical engineering experience in switchgear design, commissioning, and troubleshooting, power system protection, and power system grounding. Sergio continues to actively increase awareness on electrical safety on a global front. Sergio is a senior member of the IEEE, member of the IET, and has been awarded consulting engineering status with the PEO professional body. Sergio is a member of several industry working groups, and he is the author and owner of several US patents related to electrical safety. Please welcome to Sergio.
Thank you, Miriam. Thank you, everyone. I hope you're all working safely from a location where you can work safely from. Today, we're going to discuss resistance grounding in data centers, and we're going to use these safety codes and installation codes for North America, primarily the Z462 and NFPA 70E, both the 2021 versions for electrical safety in the workplace, and the National Electrical Code and the Canadian Electrical Code. And we're going to see how they help us apply our technology into the workplace, as well as use it safely so that no one gets hurt. And ultimately, we don't want anybody to get hurt. So in the United States, National Electrical Code 230.95 says you must have ground fault protection on systems that's rated 150 volts to ground and greater than 1,000 amps. And you must put ground fault protection in all the disconnecting devices. And you guys probably already know this with the LSIG function of your breakers. And it's predominantly low voltage breakers, but this can apply to medium voltage breakers as well. Well, not exceeding 1,000 volts, but so 230.95A says ground fault protection system shall operate to cause a service disconnect to open all ungrounded conductors of a faulted circuit. This is predominantly a ground faulted circuit because the maximum setting of the ground fault protection shall be 1200 ampere. The reason that we have to disconnect an electrical circuit when there's a ground fault and specifically have LSIG functionality on a disconnect is because ground faults can often go undetected and can cause fires if they're not eliminated quickly. So as you can see here, the maximum time delay shall be 1 second for a ground fault current equal to or greater than 3,000 ampere. So the Canadian Electrical Code has the same thing. 150 volts to ground, 750 volts phase to phase, 1,000 amps or more. And it basically says the same thing: 1,200 amperes, 1 second maximum ground fault current, and shall not be greater than 3000 amps. So let's take an example and see what happens in a solidly grounded system where we have in this particular example, a 2000 kVA transformer, 5 kV primary, and for this one I use 277 480 volt secondary. So you can see we have a 2400 amp full load current on the system, so we have a 2400 amp main breaker. We have two particular feeder breakers on this scenario, 800 amp and 600 amp. There could be more. This is just show part of the circuit. The three-phase bolted fault current on this, using a strict rule of thumb, is going to be around 48,000 amps. So if you have a full three-phase bolted fault current, you can get as high as 48,000 amps. If you get a ground fault on one of the phases, the ground fault current can be as high as 34,000 amps. So obviously it's going to be greater than 3,000 amps. But this is the maximum current that can flow in a single phase to ground fault if one should happen at this location, and not including an extraordinary amount of impedance in the fault. But let's take a look at what happens on the primary of this. Once we have a ground fault on the secondary, more often than not, the primary circuit also trips because we're getting 2.3 kA of amps on two of the phases of the primary to feed this current on the secondary. So chances are we're going to blow a couple of fuses over here because of a ground fault over here, and because we're feeding all this current to this transformer, we're going to get line voltage dips. So I don't know if any of you have this book, but it's an excellent book, Industrial Power System Grounding Design Book. And according to Dunky Jacobs, Mr. Shields and Mr. Conrad St. Pierre, who incidentally, as Miriam said, I've had 3 decades of experience in the field. I met all of these gentlemen, and I can't hold a candle to what they know about grounding. According to them, most faults begin as single phase to ground faults, and they propagate to phase or 3-phase fault. If you have a solidly grounded system and you have a ground fault, you have to imagine that you have a tremendous amount of energy deteriorating the insulation around the point of the fault. So you can have molten steel, molten copper, all kinds of debris deteriorating the insulation, because in 600 volts or below, or anything less than 1,000 volts, the primary insulation is air. If you deteriorate the air, then you deteriorate the insulation, and you can have a phase-to-phase and or 3-phase fault, which all started from a single phase to ground fault. Now remember, it takes time to eliminate the single phase to ground fault if you have the maximum amount of fault current. If you don't have the maximum amount of fault current and have the minimum amount of fault current, you may not necessarily trip at all. Can everybody hear me? Because I got a question that said somebody can't hear. Miriam, can you hear me?
Yes, Sergio, I can hear you.
All right.
Yes, I was wondering the same, but
all right, thank
I can
you.
hear you perfectly.
So by limiting the fault current to a low value, so the National Electrical Safety Codes, Z462 and NFPA 70E, and these are the most current versions. They changed so slightly this year, but they always improve. Now, keep in mind that one of the questions I get asked the most is, do you have to follow NFPA 70E and Z462? Because they are not installation standards, they are safety standards, so they always apply. It doesn't matter when your installation was built or was assembled, these standards, the safety standards, apply to all installations all the time. So design engineers and consultants have the obligation to eliminate hazards or reduce risk by doing the following: reduce the likelihood of exposure, reduce the magnitude or severity of exposure, and enable achieving an electrical safe work condition. And regardless whether you're Z462 or 70E, both of these and 0.2.2 are exactly the same. 0.2.3 is also the same. The following methods have been proven to be effective in reducing incident energy. Zone selective interlocking, differential relaying, energy reducing maintenance switch with a local status indicator, energy reducing active arc flash mitigation system. This is a new one this year, energy reducing line side isolation. And this is new for both NFPA 70E and Z462. So what it does is it includes another barrier between the line and the load side of your main incoming breaker. Arc flash relay, high resistance grounding, current limiting devices, and shunt trip. All of these protective measures, other than number 7 or G, reduce incident energy, but they only come into effect after the fault has occurred. So they reduce the time that the fault is on the system. And when you reduce the time that the fault is on the system, you reduce incident energy. Because according to IEEE 1584, incident energy is directly proportional to time. If you can cut your clearing time in half, you reduce the incident energy by a factor of 2. High resistance grounding is the only method which prevents the probability of having an arc flash, because as the book indicated, most faults begin as single phase to ground faults and propagate to a 3-phase fault. So although high resistance grounding does not reduce incident energy, it is an arc flash mitigation technique in that it reduces the probability of having a single phase to ground fault propagate to a 3-phase fault. So 7 of the electrical safety standards says a great majority of electrical faults are of the phase to ground type. High resistance ground, you will insert an impedance in the ground return path and will typically limit the fault current to 10 amperes or below on systems 5 kV or less, leaving insufficient energy and thereby help reduce the arc flash hazard level. Doesn't reduce the incident energy, but it reduces the arc flash hazard level. High resistance ground will not affect arc flash energy for line to line or line to line to line. Remember, when you do an incident energy study, you're going to be looking at the 3-phase bolted fault current that's available on that system. High resistance grounding does not change the magnitude of the 3-phase bolted fault current. So the NEC has a high impedance grounded neutral system. A high impedance grounded neutral system in which a ground impedance, usually resistor, limits the ground fault current to a low value. So although the United States does not limit or define a low value, it is understood that 10 amps or less is a low value, provided that the service conditions of maintenance ensure that only qualified people service the installation, ground detectors are installed, and line to neutral loads are not served. Another important factor is they put an information note in NFPA 70, the National Electrical Code, It says, according to Annex O of NFPA 70E 2018, standard for electrical safety in a workplace, high impedance grounding is an effective tool to reduce arc flash hazards. So it's very important that they put that in there, because now you know that you can employ a high resistance grounding system. It doesn't necessarily say you need to interrupt the service if you have a ground fault. Because 230.95 said that if you had a system that's 480 volts or greater than 150 volts to ground and greater than 1,000 amps, you must trip. But this clause says that if you're over 480 volts to 1,000 volts, you don't have to trip at all if you limit the fault current to a low value. So let's see how that looks now if we have a resistance grounding system. Same transformer we had before. Full load current of 2400 amps, 48 kA bolted fault current, even though there's an impedance over here. So that resistor on this system, we limit that fault current to 5 amps, is a 55 ohm resistor. 277 divided by 5 amps equals 55 ohms. A 55 ohm resistor protects everything on the secondary of that transformer, right down to the very last 1 horsepower motor. Everything on the entire secondary is credited with an arc flash mitigation technique because of this resistor, which is smaller than a bread box. Again, I'm showing my age because nobody has bread boxes anymore. We have the same ground fault. Actually, we changed phases on this particular fault. We're on C phase now. Now, when we have a ground fault, the ground fault current changes to 5 amps. It used to be 34,000 amps. Same transformer. Inserting a 55 ohm resistor limits that fault current to 5 amps. That means we don't have to trip. And we have continuity of power, which is extremely important for data centers and many, many other industries, but we're going to predominantly talk about data centers now. What happens on the primary? We get an additional 0.3 amps of primary current for this 5 amp current on the secondary. So we have a ground fault on the system now, and we want to be able to find it without shutting anything down. So what we can do is, if we change the value of this resistor, we change the fault current. If we have a 55 ohm resistor here, we change the fault current to 5 amps. Let's assume we change the value of the resistor to 110 ohms. We change it to 110 ohms, the fault current is now 2.5 amps. Now let's say we do that cyclically. 1 second, we have a contactor here, and we change the value of this resistor from 55 ohms to 55 ohms, to 110 ohms, and back to 55 ohms, and we do that cyclically. So for 1 second, there's 55 ohms. For another second, there's 110 ohms. So when we have a fault, we can actually let that fault tell you where it is by locating it. We have a ground fault on C phase. The ground fault current path is here. This is the bonding network. Don't think of ground. We don't use ground as a return path, but this is the bonding network that we have, and that doesn't change regardless of what type of grounding system you have. That fault current only exists in this faulted path. So anywhere in that path, if we turn on the pulsing and we change the value of that resistor, we're going to see a fluctuation in the current if we put a 3-phase CT or CT around all 3 phases of the system. We're going to follow this signature right down to the very point of the fault. As soon as we pass the point of the fault, when we're here, we're going to see normal phase current. So we know that we've either passed the fault or the fault doesn't exist anymore. we can go back and find where the fault is. And I've had this challenge with Southern Ontario and many other jurisdictions throughout North America that if I can't find a fault in less than 1 hour, I will buy lunch for everyone in the facility. I have never had to buy lunch for anyone in the facility because we can always find the fault in a short order of time. And we don't have to open up any doors to go around the three-phase conductors because our equipment is so sensitive, we can actually pick up current around conduit or around bus duct. So we don't have to open up. We have an arc flash mitigation technique. We didn't shut anything down because while this fault is on the system, nothing has been shut down. Everything continues to work. This is why we have so many high resistance grounding systems in data centers all over the world, but we're discussing North America right now. We have some of our resistance grounding systems in some installations that claim that they will lose $1 million a minute if the power was shut off. So much so that the entire industry, that bank, would go bankrupt if there was 3 consecutive days of no power in that system. So they rely on this system. So in this example, I'm going to turn on the pulsing on this system. That's a three-decade experienced thumb pressing that button, okay? So we're going to turn on the pulsing. And what's important here is try not to pay attention to the digital number. I understand we're all engineers. We want to focus on that digital number because we think it's more accurate than anything else out there. Try not to look at that digital number because you'll drive yourself nuts. Instead, look at this bar graph underneath the digital number and you'll see it moving at the same rate that we're pulsing or changing the value of that resistor. That's telling us that the fault is downstream from our location. You've heard the expression that current takes the path of least resistance. Oh, I apologize. Current takes every single path that's available to it. So if you take a look, I'm right around an elbow over here. So I can actually determine that the fault is downstream from this location, even though I didn't have to open up any doors and place my employees in harm's way to find where that fault is. So I can go around bus duct and tell you exactly which drop has the ground fault. And so you can find the fault very, very quickly with this type of system. In this example, we created a three-phase arc fault with a resistance grounded system here and a solid grounded system here. Now to create an arc fault, we had to place a piece of 18 gauge wire on all three phases, turn on the power, and when the power was applied, that 18 gauge wire disintegrated, and then we see this. As you can see, there's less damage that occurs on the system that's resistance grounded as opposed to the system that is solidly grounded. So much so that when we did an installation on a particular manufacturer who had 100 substations that were solidly grounded, they decided that they were going to change 100 of these substations from solidly grounded to resistance grounded solely as an arc flash mitigation technique. Now this was done in 2010 through 2014. So at the time that they did this, they were following the 2004 guide for calculating arc flash incident energy. And unfortunately, During that time, because 1584 penalized high resistance grounding by assigning a higher incident energy than a solidly grounded system, which is not true, it has been rectified, they decided that it was worth their while to change 100 substations from solidly grounded to resistance grounding as an arc flash mitigation technique and install some arc flash mitigation relays to reduce the time that the fault was on the system. And what they found is that after the installation of from 2012 and 2014, they had some motor repair costs in systems that has not been converted yet to resistance grounding. But after the installation of the conversion of all the substations to resistance grounding, their motor repair costs reduced from $500,000 or $250,000 to virtually nothing in 2015, 16, 17, 18, and unfortunately, we don't have anything from 2019 and 2020. But their motor repair costs reduced greatly because when you have a ground fault on a resistance grounded system, the damage at the point of fault is so greatly reduced that you don't damage the equipment where the ground fault is. So in comparison, when you have a ground fault on a solidly grounded system, you must trip. On a resistance grounded system, you don't necessarily have to trip. Serve line to neutral loads. Yes, you can serve line to neutral loads on a solidly grounded system. Here's where we differ now between Canada and the US. In Canada, you're allowed to have single phase to ground loads, or sorry, phase to neutral loads on a resistance grounded system. However, you must trip when you have the first fault. So it really doesn't benefit you in having a distributed neutral on a resistance grounded system. Instead, you could service that 277 or 347 volt lighting with an isolation transformer. So if you put in a 112 kVA transformer from 480, 480, 277, or 600 to 600, 347, now you can service the lighting load. And what ends up happening is you end up with a safer system, primarily because now your electricians who were exposed to the three-phase voltage fault current when changing the ballast of a 480 volt system from a 2000 kVA transformer, and we saw that current to be 48 kA, now they have the voltage fault current coming from a 112 kVA transformer. So you'll find that you end up with much less incident energy where your electricians are going to be doing most of their work in isolating or changing ballast. For safety, they're both safe. No one is going to tell you that a solidly grounded system is unsafe. I'm telling you that a high resistance grounded system is safer, as long as the entire load on that system is compatible with the resistance grounded system. And we've done some installations when we've converted some plants in Toronto, shall we say, from solidly grounded to resistance grounded. And there was a data center, and unfortunately, a lot of consultant engineers believe that if one surge protective device is good, then 100 of them must be better. And when you put in 100 surge protective devices on a high resistance grounded system, it doesn't matter how many surge protective devices you put in. If they're not compatible with the high resistance grounded system, they will function. They don't fail, they do what they're designed to do. So when you have a resistance grounded system and you use surge protective devices that are designed for solidly grounded systems, the two unfaulted phases elevate above ground, and the grounded phase and ground are at the same potential. So if you had a 480 volt system the 480 volt unfaulted phases, say A and C phase, are at 480 volts with respect to ground. If your surge protective device is designed to trigger at 400 volts, you haven't done anybody any favors by using a surge protective device which is employed for a solidly grounded system for use on a resistance grounded system. This is why when you specify a variable frequency drive or adjustable speed drive or a surge protective device, you must tell your contractor, your distributor, you need a 480 volt or 600 volt surge protective device capable of handling 200 kA, designed for an X grounded system. And that X grounded system is going to be solidly grounded system if you have a solidly grounded system, or it's going to be high resistance grounded if you have a high resistance grounded system. So the high resistance grounded system will work on the solidly grounded system. The solidly grounded system, unfortunately, will work on the resistance grounded system, but not the way you want it to. The cost of a solidly grounded system, I have this question all the time. Is it cheaper to put in a resistance grounded system or a solidly grounded system? So the cost of a solidly grounded system is higher initially, because you have the cost of the 3-phase 4-wire system, that 4th wire, running the installation, running the cables for that 4th wire, putting in the G function of the LSIG. All that adds up when less than 10 to 15% of your load is going to be single phase with the distributed neutral. Why do you have to run all those conductors for 15% of your load being 3-phase 4-wire? Instead, you could put in an isolation transformer and probably end up with a less cost. Reliability. With the solidly grounded system in data centers, because we understand that when you get a ground fault, it is understood that you must trip. We tend to put in more redundancy. And just because you end up putting more redundancy in a system doesn't make it more reliable. It just means you have more things that can fail. Adding redundancy does not increase reliability. And believe me, this is a feature that we've learned because we have some products that are considered extremely safe products. So they have a safety integrity level of 3 or higher. Adding more components to increase the reliability does not increase the safety intrinsic level. You have to ensure that the right components are in, not more components that can fail. So if you have a data center, you can actually put in a 2n+2 or an n+1, but that's adding redundancy. It's not adding reliability. Putting a resistance grounded system is increasing reliability because you do not have to trip when there is a ground fault. And the ground fault is the most common occurrence in the electrical industry on an installation. The other benefits, reduce burning and melting effects. This is always a very good thing to happen in your electrical installation. You don't want things to burn and you don't want things to melt. So limiting the energy on a single phase to ground fault prevents burning and melting. We reduce mechanical stresses. This is when you have bracing in your electrical system. You still have to brace for the 3-phase bolted fault current, but not necessarily for a single phase to ground fault. Reduce arc flash hazard to personnel. So that's a bonus because now you're protecting your employees by having a resistance grounded system. And as I said earlier, when you put in any one of those other ground or arc flash mitigation techniques, they only start to work after the fault occurs. Resistance grounding is the only arc flash mitigation technique which limits the energy or gives you the benefits of using a high resistance grounded system before the fault occurs. Reduce momentary voltage dip. You've seen when you've had a ground fault or you start a large motor, the voltage dips to some degree and something can happen after that. With resistance grounding, you're not going to get that as much because you don't have such a strain on the primary due to the inrush of current on the secondary. So we have standard high resistance grounding systems. In standard high resistance grounding systems, at a minimum, you must have a resistor to limit the fault current. So this resistor over here. You may or may not have pulsing because unfortunately the NFPA 70E and Z462 just says use high resistance grounding system, but they don't necessarily mean all the benefits of that. So we've had people who put in a high resistance grounding system, just put a straight 55 ohm resistor on the neutral to ground, put a CT on there and call it a resistance grounding system, slap on an arc flash mitigation technique on it and say they're happy and they're gone. But it doesn't do anything for them because it doesn't tell you where the fault is. You could put an ammeter to determine whether you have fault current in that return path. Because remember, when you have a ground fault on a resistance grounding system, all ground fault current must return back to the source. So by putting a CT right here, we're measuring all the return current that comes back to this point and back to the transformer. You could put a voltmeter on here to measure the voltage across the neutral to ground bus and the pulsing contact. So if you had a typical data center topology, and this is what I've drawn here. You've got the transformer, and you've got the generator, only one of these on at any one time. And you've got your distribution. So you need two high resistance grounding systems if you use the standard high resistance grounding topology. One for this resistor, one for this resistor. And depending on which load is on, or which source is on, that's the actual high resistance grounding system that's active at that point. The resistor will only limit the fault current when it's on the system, and this system here will tell you have a ground fault if this breaker is closed. If this breaker is open and this breaker is closed, you have to go to this system. So you're probably looking at two different locations to determine if you have a fault on the system or not. Because normally the utility transformer and the generator are not in the same building. But if you had a smart high resistance grounding system, we go a step further. You still have the resistor over here in the pulsing contactor, but we're able to detect if you have a fault by monitoring the voltage on the bus. And if you can monitor the voltage on the bus, it doesn't matter where the fault is. The fault is always going to be in the loads. If the fault is in the loads, we tell you what load or what feeder that fault is in. So we give you feeder indication. It's easier to find the fault because I tell you where to begin looking for the fault. You have an option for resistor monitoring. One of the things that's in the Canadian Electrical Code is that you have to monitor the resistor for electrical integrity, which is not necessarily performed in the United States. It's easier to find the fault. We have adjustable timer. So we've had some customers that say, I'm going to give my electricians 8 hours to find the fault. If they don't find the fault in 8 hours, I'm going to trip this device. Just so the electricians have something to do, I would imagine, because electricians are always busy. But if you say they don't have to do anything when there's a fault, they will not do anything when there is a fault. If you give them a time limit of clearing that fault, now they'll go out and find it. And we have an arc flash monitor that you can have in this. One of our customers came to us and said, I like the idea of putting in a resistance grounded system. However, I don't like the idea that I don't get to put a label on my equipment that has lower incident energy. Why should I spend $5,000 to $10,000 on a substation and not get the benefit of putting a new label on there that has lower incident energy? So what we've done is we've created an arc flash relay, which is integral with the resistance grounded system, and we can trip in 1 millisecond if we detect the presence of a fault. So now you can have an arc flash mitigation technique where you can lower the probability of having a arc flash event and lower incident energy. And as the manufacturer of the resistor and the relay, we have the capability of doing that. So now our topology changes. We can have a resistor on the transformer, a resistor on the generator, a smart HRG system on the bus. So this is where our HRG system is. To me, this resistor is just a return path. The only thing I'm going to use that for is if the generator is on, the return path current is through the generator. If the utility is on, then the return path is through the utility. As far as the HRG system is concerned, it's irrelevant what the source is that's on. I'm looking for the ground fault current in the load because most of the ground faults are going to be in the loads and not the sources. The sources get the added benefit of being monitored and protected, but I'm more concerned with the loads. So in this particular example, we have a full-blown smart HRG system. So I could have a fault over here, and I can say that that fault is on feeder 6. So already I start the pulsing. I could start my pulsing at feeder number 6. If you had a conventional HRG system, you would actually start the pulsing, determine which breaker was closed, and then start looking here for where your fault is, or here. And so my competition likes to put out these flyers that say they have trending and historical events and logging, but really all they're going to log is they have a fault, they don't have a fault. The fault is back, the fault is gone. With my system, I tell you, you have a fault, the fault is on feeder number 6. You have a fault, the fault is on feeder number 5. So it gives you more information about what to do when you have that fault on the system. With generators, say for example, we've had some instances when we had many generators on a synchronizing bus. If you put a high resistance grounded system on each one of the generators, in this particular example, if you have 4 generators on a 600 volt system or 480, if you put a 5 amp resistor on each generator, if all 4 generators are running, you're going to have a maximum fault current of 20 amps. What happens if you have a fault current of 20 amps is you don't get the benefit of staying online if there's a fault on the system. You don't get the benefit of having an arc flash mitigation technique. So what we've done is we've employed a zigzag transformer on this bus, and you can put a small resistor on each generator, limit the fault current to 5 amps, so it doesn't matter which particular or how many generators you have online, you always limit the fault current to 5 amps. Now you can put pulsing on here, and you can actually enjoy the benefit of having an arc flash mitigation technique, not trip when you have a ground fault, and continue operation when you have a fault. Same thing for medium voltage generators. If you have 5 kV or 15 kV, you can actually employ resistance grounding, not necessarily high, but maybe low resistance grounding system on the bus, limit the fault current, and then continue. So we have a new display now that comes with these units, and it has more information. We have trending. We monitor the voltage on the bus, and if we see that the voltage on the bus has two phases that elevate above ground by full face-to-face potential, and one phase which decreases with respect to ground to a lower value, and more importantly, the neutral shifts. Even though we don't actually monitor the neutral, we monitor the apparent neutral in this system, and we can determine if there's a fault on the system that way. And we monitor the current. So this is why we tell you we can determine if there's a fault, what phase the fault is on, and what feeder the fault is on, because we're monitoring the current going this way. If we see the voltage escalate and there's no current flowing, we tell you that there is a bus fault on the system. That means the fault is on the line side of all those feeders. So it's either in the transformer or it's in the generator, and seeing as only one of those breakers are going to be closed at any one time, you know it's going to be between here and here. So we tell you where to start looking for the fault, even though the fault is on the line side or inside the generator or inside the transformer. We tell you there is a fault, it's on the line side, it is considered a bus fault. The transformer secondary and the generator is still protected by the same high resistance grounded system. There's a fault on feeder number 3. We say that there's a fault on feeder number 3. But if you get a second fault on a different feeder, on a different phase, then we say there's a fault on two phases. These two modules communicate with each other, and the one that you program to be of a lower priority will trip first, keeping your critical processes going all the time. This is why we use high resistance grounding systems in data centers, in hospitals, in pulp and paper facilities, in petrochemical facilities. You can have monitoring, everything on a glance. You can monitor the integrity of your health. So much so that some of our customers came up to us and says, I'm going to put this on a standby generator, but I don't want to hear the alarm go off because the voltage on a standby generator is always off unless it's on. But the predominant voltage on a standby generator is no voltage at all. So we put in a generator mode so that it doesn't alarm all the time if the generator is de-energized. So at a glance, you can tell what the fault current is and what the priority is on any phase or any feeder. We tell you any of the history that occurred, a fault occurred, a trip occurred, and trending. So you can actually trend a line, a feeder, and determine how it's doing and if it's trending to be more deteriorating than others, because you'll see this time period change and you have selectability over this time period. So this could be like 2 years and you can see it changing and determine if you need to act or not. So this is basically maintenance by exception as opposed to maintenance by routine maintenance. But one of the things we've also discovered is a lot fewer people are being hurt by arc flash mitigation. The more people are being hurt by shock than anything else. So we've developed a absence of voltage detector. And what happens with an absence of voltage detector, if you look at terminology in 70E and Z462, they say you have to establish an electrical safe workspace. And before you can do that, you must measure the voltage face to face and face to ground, both AC and DC, and only after you've ensured that your meter works and you have a low or no voltage, determine that it is de-energized or there is an absence of voltage. What this device does is if you have all three red LEDs, that means the voltage is present on your system. When the voltage is not present, all that happens is you lose the presence of the three red LEDs. So you press the test button, the unit is going to go out and test face to face, face to ground, AC and DC, and determine that, yes, there is less than 3 volts face to face and 3 volts face to ground, both AC and DC, and I've checked the meter for functionality. Therefore, I can show you 3 green lights. It is safe to enter this particular gear. The other thing we've done is we have the world's smallest footprint original OEM HRG system. And this is what it looks like. We have a LCD display, which gives you the voltage and the current across the NGR, or neutral grounding resistor. And we have this particular device that monitors the health, safety and health of the neutral grounding resistor for Canada, and there's a way of disabling that function for the United States. So we can actually, this is no larger than a page of paper. So this is about, what is it? 8 inches by 12 inches. So this is like the world's smallest OEM HRG system, because we supply these to all other OEMs as well. And with that, I'll open the floor to questions.
Okay, thank you, Sergio. We have many questions here, which is good. So let's go with the first one. Okay, for 2 HRG systems, are we going to interconnect them on ground side?
Everything gets connected to the ground side, yes. The ground, there's only one ground in any facility, and it is ground. Everything gets connected to the same ground. So 2 HRG system, you could have an HRG system and an LRG system. So a 4160 volt to 480 volt transformer and a 480 volt to, well, let's say, for example, you have a 13.8 kV to 4160 volt transformer. You could put a low resistance grounding system on that transformer. So you have a 6 ohm resistor. So that neutral gets connected to ground through a 6 ohm resistor. That system feeds a 4160 to 480 volt transformer. And you want to put a high resistance ground on that one. You could put a 5 ohm resistor on the neutral and connect it to ground on the other side. It's the same ground that the 6 ohm resistor is. Now you're going to have a 480 volt to 120, 208 volt transformer to service lighting. So you can plug in a laptop or a computer. It's the same ground. That's going to be a solidly grounded system. Everything is the same ground, but if you have a fault on the 480 volt high resistance grounded system, all that fault current returns back to its own source. It's going to use the ground path that's in the system, but it's always going to return back through that 55 ohm resistor. So the neutrals are different. The ground is always the same. I hope
Okay.
answers the question.
Okay, we have another question here. In the demo video, did it show 3-phase fault? Resistance grounding would not make any difference, right?
No.
Demo should be single phase to ground for both. Solid grounded probably propagated to 3-phase, correct?
Yes, you're talking about this video. Yes, it's a phenomena, but I like the way it looks, so I'm leaving it in here. Tell him he's right, but the video has its effect on here. There is less damage that occurs on the resistance grounding system. You're right, it should not have any effect on the system. So how do you explain this?
Okay. Next question is, for the typical data center topology, does the generator need a fault detection system as well? Is it not redundant if there is one for the main transformer? The HRG on the generator purposed for reducing the high ground fault current a generator can undergo?
Okay, so this is for the Canadian Electrical Code, right? As far as I know, it says if you employ a high resistance grounded system or any resistance grounded system, you must monitor the integrity of the resistor. I don't think they differentiate between normal and generator. So if you have a normal system, you must have monitoring for this resistor. And if you have a generator, you must have monitoring for this resistor. So I think you have to have monitoring for each resistor that's on the system, because if the generator breaker is closed, that means, well, obviously these are interlocked. You don't parallel. So this is the utility breaker is open, the generator breaker is closed. And I think because you're on generator, this makes this now extremely crucial that you must have monitoring on the generator. So I don't think you can differentiate between normal and generator. If you have a resistance ground in the system, I think the Canadian Electrical Code says you have to monitor both.
Okay, thank you. Next question is, what is the difference of installing a CT on the neutral side versus the ground side of the NGR?
A CT, there's no difference at all. You're measuring the current going through the resistor.
Okay. Next question. Comparing two grounding systems, solidly grounding is more expensive than high resistance grounding system. But my understanding is high resistance grounding systems need isolation transformer and resistor, while solidly grounded is only need bonding wire, which is number 6 AWG, right?
Well, if you're getting your system from the utility and you don't have your own transformer that's feeding your plant, then yes, solidly grounded system is probably the only thing you can do. This is why if you're going to put in a resistance grounded system, you don't want your fault to interfere with your neighbor. So you are going to have your own transformer. So these are facilities that have their own transformers though. If you have a strip mall, for example, one store in a strip mall can put in high resistance grounding system because you're sharing your ground with all your neighbors. So if you have a transformer, the cost of employing a resistance grounding system is more cost effective than employing a resistance grounded system is more cost effective than a solidly grounded system. That's what I'm saying. If you are getting 600 volts or 480 volts from the utility directly and you have no control over the transformer, you're going to get whatever they give you. You have no choice at all. I hope did that answer your question?
Okay, let me see. We have some more comments here. Not yet, but we do have another question. Does HRG only apply to face to ground, not face to face, correct?
Correct. Are you asking me or are you telling me?
No, it's a question.
Okay. That's yes. HRG only affects the phase to ground current. It has nothing to do with phase to phase current. But remember that book I showed you earlier? That book says that up to 95 or 98% of all faults begin as single phase to ground faults, and then they propagate to phase or three phase faults. So much so that they're saying 98% of all faults are single phase to ground type. 1.5% 1% are phase-to-phase fault, and 0.5% of all faults are three-phase bolted faults. As a matter of fact, it is very difficult for a three-phase bolted fault current to occur all by itself, unless, and I hear this more often than not, somebody leaves the grounds on after maintenance and you energize the gear, or you open up a panel and steel falls across three phases. A forklift drives through a bus duct. It's very rare that it's going to occur by itself.
Okay, thank you, Sergio, for presenting today's webinar. It's time to close the session up. Thank you to all of attendees. You will receive a follow-up email shortly with a link to the recording webinar.
Okay, but
have a great day.
I don't think we answered all the questions. So what we'll do is we'll address all these questions and pose them on our website, so you have the answers to them. We're not going to ignore the questions if they weren't answered live, but we will answer the questions.
Oh, yes, that's correct. We will provide a Q&A document, and it will be posted in our website. Okay, thank you. Thank you all, and have a great day, and stay safe. Sergio, are you still there?